Welcome back. This is the continuation portion of the cylinders. This is where we're going to talk a little bit about formulas. At the end of this, you're going to see some of your assignment questions, attendance assignments for today. So the first thing we have to look at is cylinder factors. Cylinder factors tell us how much gas is leaving the cylinder per 1 psi drop. Every time you lose 1 psi, you lose this much gas. And so the first thing we have to look at is the cubic feet when full. So an E cylinder, for example, is 22 cubic feet. An H cylinder is 244 cubic feet. When we use the pressure, we use 2200 psi. We have to get the cubic feet into liters, okay? And in order to do that, we're going to take 1 cubic foot of oxygen is equal to 28.3 liters. And you can see this is an English metric conversion, and this is how we do it. And so the cylinder or tank factor is the size times the 28.3 and then divided by the pressure when full. So here's your E cylinder. There you see your 22 cubic feet of O2. We use the full pressure, 2200 psi. So we're going to take the 22 cubic feet times the 28.3 liters per cubic foot divided by that 2200 psi is going to give us 0.28 liters per psi. Okay, so that's how you find these. And for the most common cylinders, we actually have these. And these are something that you don't have to find every time. Basically, what you need to do is just memorize them. So we can show you the one on the H cylinder also. So you can see the size, 244 cubic feet. Again, the pressure, 2200 psi. Once we solve it, it's 3.14 liters of gas is leaving for every drop of psi. So basically in the hospital, when you're looking for how much gas is left, we're still going to use those cylinder factors, but when we use the formula for finding how much is in the cylinder, how much gas is in the cylinders, then we're going to go ahead and we have to subtract 500 for the hospital requirements, okay? So there's your cylinder factors, DEs, GJs, HKs. Be aware of these. These are on your boards, okay? So do know those cylinder factors. So to find how much gas remains in the cylinder, like I said, you're going to take 500 away from how much psi is in that cylinder. You're going to take your cylinder factor and then the flow, and you're going to multiply and divide. So the formula basically is psi in the cylinder times the cylinder factor divided by the flow equals minutes. If you come up with anything over 60 minutes, now you can turn this into hours. And how do we do this? We take the minutes, which is your initial answer, divided by 60. That gives you hours. With your E cylinders, for the most part, they're not going to go over 24 hours. They're probably not even going to reach 24 hours. But if your cylinder is big enough and you're not using as much, you can go into days. And so how do we solve for days? We're just going to take those hours that you have divided by 24. That gives you the number of days. So what do you do with the part that's behind the decimal? Well, one thing you can do if you want to, if it's low, say 10, 15 or something like that, toss it. Don't worry about it. If it's 0.5, that's basically almost close to a half hour. What you can do, if it's hours, you multiply by 60. If it's hours, days, then you multiply by 24. So whatever you divide it by is what you're going to multiply, okay? And then remember, you cannot round these up. They have to go down because you can't add any more gas to the cylinder. So here's an example. We have the duration of an E cylinder, has 1250 psi. Patient flows 3 liters per minute. They're in the hospital. You have to leave 500 psi. This is a requirement for the hospital, okay? So 1250 minus 500 gives you 750. The cylinder factor for an E cylinder is 0.28 liters per psi. So you're going to multiply it by that 0.28, come up with 210. At this particular point, you've got 210 liters per 3 liters per minute. Now you're getting rid of the liters, and that's how your minutes come up at the end. So at this point, it's 70 minutes. 70 minutes is really, really easy. 60 minutes is an hour and 10 minutes. That's all you have to worry about, okay? And if you wanted to, you could drop that 10 minutes and say that's your fudge factor. Here's another one. In this case, there's more PSI, 1550. The patient flow is 15 liters, so using quite a bit. In this case, you're still going to do the same thing. 1550 minus 500 is still an E cylinder, so it's 0.28. Divided by the 15 comes up to 19.6 minutes. 0.6 I'm not worried about. I'm going to kick it off at that point. So now my answer is only 19 minutes. This one, this is a person who's outside the hospital can do anything they want with their cylinders. They can change it at any PSI they want to. And so this is a case of a duration of an E cylinder that has 1100 PSI. The patient flow is at 10 liters per minute. And this time we're not leaving anything. So it's going to be the entire PSI times the 0.28 divided by 10 comes to 30.8 minutes. 30 minutes, close enough. I'm not worried about the seconds. Okay, so here's the duration of an H cylinder, PSI 1750. We're going to leave 250. The flow is 7 liters per minute. Work all of this out. You come up with 11.2 hours. How many minutes is 0.2? It turns out to be 12 minutes. Wouldn't say, oh, you've got 12 minutes to do this. I would just go ahead and say you've got approximately 11 hours. Same thing, more pressure, leaving everything in the cylinder at this particular point. Comes to 8.7 hours. How many minutes is 0.7? It's 42 minutes. You can tell the patient if you want to, they have 8 hours, 42 minutes, or just tell them roughly you get a little over 8 hours. Just build your own fudge factor into it. So liquid systems, a little bit different. Remember, liquid systems have to be weighed, okay? Because remember, as long as there's liquid in the cylinder, we're going to keep that pressure. It's going to stay the same. So what they use for the most part with the liquid systems in the hospital or the bulk supply, these are much, much cheaper than having all these small cylinders. If you remember, 1 liter of oxygen will expand 860 times. If you're using, say, 20 liters a day, what's 20 times 860? That's how many cylinders that you're going to have at that point. Along with that, your liquid oxygen is stored at about a negative 183 degrees Celsius. It's continuously vaporizing. If you go up to the hospital and you ask to see the bulk system and they take you out, you'll sometimes see a lot of ice crystals, if you want to call them, around the bottom, and that's the vaporization from that lock system. There are pressure relief valves in the system. The key to this is you got to use more than you allow to evaporate. If you're not using more than what you're allowed to vaporize, which is evaporation, then unfortunately it's going to cost you a lot of money. And your insurance company, if they're paying for something like this, is not going to pay for it way, way too much. So you have to use more than you lose, okay? And these systems have to hold at least 20,000 cubic feet of gas. And that includes the reserve systems also. So this is a picture of a bulk, and as you can see, there's a main unit and then there's a backup to it. One of the requirements, and you're going to see this in a couple of slides, is you have to maintain the average of 1 day backup for your system. That way, if you lose the main system, you still have the backup system for it. And this is just showing you 2 different drawings of it as far as that goes. As you can see, there's your liquid at this particular point, very cold. What we're going to do is we're going to warm it up. Here's the heat exchanger, and then we're going to turn it into a gas. Converting it into a gas, we put it into the piping system, and now we're able to deliver it to the patients. So why do we have a bulk system? Well, first of all, you don't need as much storage area, and that's really, really important. There's certain requirements about where you can store cylinders, and you can have them, but somewhere around like 5 feet away from sidewalks, 10 feet away from churches and schools, different things like that. So, depending where your hospital is, you'd have to be in the middle of a baseball or football field if you're going to try to do cylinders for the most part. The initial expense will decrease over time. If you've ever run a business, you know that you have a high cost startup and then it becomes cheaper as you go on to it. There's less prone to interruption. It eliminates the inconvenience. There it is. And we can regulate the delivery pressures centrally. And so we don't need a relief system on top of all of these. We just need the ones that we need to be able to control it at that particular point in time. So there's different systems that you can have. One is an alternating gas supply system. This is where you can actually get away with large cylinders. Your hospital's not that big. It could be just a little clinic somewhere, a little bit bigger than, say, the CVS clinic or one of the other little clinics that we have, but not big enough for a hospital. So what you can do then is you have two banks of cylinders. One is a primary, one's a reserve. Once you reach a preset pressure level, you have a control valve that's going to switch over, and now the reserve becomes the primary. Once you fill the old primary, it now becomes the reserve. And here's just a little picture of it. It shows you how you can see that switch over. You can have a gas system with a reserve supply system. This one you can have the primary, secondary, and the reserves. Same thing. You have a system that turns an alarm system. It signals the changeover of these systems and allows the refilling to occur. Now, one thing, and I'm going to mention it here, and it doesn't really matter where it's mentioned, is this. Every now and then, what they do, what the hospitals will do, is they're going to go ahead and test their systems and make sure their systems can kick over. The most embarrassing portion of this, if you want to think about it that way, is when the reserve system doesn't kick in. And does this happen? Yes, it does. And so sometimes you have to be prepared to do something else, and that is to get the cylinders that you have that you use in the hospital. So you'll have some e-cylinders, and you have to be able to know how to hook them into what we're going to talk about, your zone valves, and repressurize that system so that you can get some oxygen delivered to your patients. There was a hospital one time that had a system. One of the therapists was working there. They went to give a breathing treatment to one of the patients. They were going to use oxygen to do it. Turn it on, and no oxygen came out of the system. He went up and he was looking at the alarm, because it's an alarm at the nurse's station in this case. And he asked them, "How long has this alarm been going off?" And they're going, "Oh, probably a couple hours. It's really annoying." And so they had lost their system for at least 2 hours. So he was out there, and it was kind of funny. He actually took a great big screwdriver with him, and couldn't get it to switch over, the system to switch over. So he was beating on the system itself to get it to switch, and finally it did switch over. He was able to get it started. So you always have to be ready in case something like this should happen. And there you can see the bulk system, gas system with a reserve. You can also have the liquid system with a backup liquid system, or a liquid system with a backup gas system if you want to. So the National Fire Protection Agency has the guidelines for construction, design, location, and there it is. You have to have reserve or backup equal to the average daily use of your hospital. Here's a manifold, and along with the alternating systems at this point. In this case, what's the blue system? And by the way, what is the brown? So here's just pictures, a liquid and liquid with a cylinder, and then cylinders with the backup cylinders. So portable liquid systems, home or intra-hospital transport, same thing, guys. You gotta use more than you will lose. Otherwise, they're way too expensive. The flow rates for these, about 8 liters per minute. They don't have 50 psi with them, so we cannot power any of our equipment. Remember, with the home diaphragm compressors, the same thing. They don't have 50 psi, therefore they also cannot be used to power any equipment. You have a stationary system. It provides oxygen therapy for 4 to 12 days at 2 liters per minute. And there you can see smaller systems. Usually that time, 1 liter will last in some cases up to 24 hours. And this is just a picture of a system, and it has its smaller system on the side there. Very fast. And this is another one. This is one of the ones that we saw first. And it's actually much smaller than this picture. So how do we figure out how much is left in your liquid system? Remember, you need to know the weight. It's filled to that specific filling density. Remember, the filling density is the ratio of the weight of the gas of the liquid now in the system as to the weight when the cylinder is filled up with 100% water. So 1 liter of LOX expands to 860 liters of gas. 1 liter of LOX weighs 2.5 pounds per liter. And there's 860 liters in the gaseous state. And so that's going to weigh your 2.5 pounds. If you divide that 860 by 2.5, you come up with 344. You can think about that. It's almost like your cylinder factor, not quite, but it's a constant. It doesn't change. So we're going to look at the amount of the gas in the cylinder, the liquid weight. You can do it this way. Liquid weight times 860 divided by 2.5 gives you the weight divided by the flow, and it's going to give you your answer in minutes. So if it weighs 1.5 pounds, the flow is 3 liters per minute. 1.5 times 860 divided by 2.5 is 516. Divided by 3, it's going to give you 172 minutes. Divide by 60 for hours, 24 for days. In the shortcut, do your 344. 1.5 times 344. Just don't have to worry about this middle portion of it, and you still come up to 172 minutes. Now, do you want to convert this to hours? Well, let me ask you this. How many of you, if somebody came up to you and said, oh, you have 172 minutes, would be able to sit there and go, oh, well, that's great. Thank you. I'm really happy you told me that. I wonder how many hours that is. So, and then your book shows that you have a fudge factor 0.8. So if you were to use that, it would be 1.5 times 344 times 0.8 divided by 3, and that came up to 137.6 minutes. So in this one, find the duration of a liquid system when the weight's 45 pounds, the flow is 4 liters per minute. So 45 times 344 divided by 4. If you come up with 3,870 minutes, if you tell that to your patient, they're going to nod their head and go, yeah, whatever. And that, because it works out to about 64.5 hours divided by 24, tells you get a little over 2 days at this particular point, okay? And remember, the weight you're using is the net weight. What is the full weight minus the empty weight? We've got to take out the weight of the cylinder. If you factor the cylinder weight in, it's going to tell you got a whole lot more left than you do. So in this one, the duration of an empty cylinder with a weight of 65 pounds. Empty weight is 30 pounds. So 65 minus 30, that's what you're going to use. Comes up to 1 day, 1 hour when you put all the math together. Okay. So there are some problems for you to practice. They're under the classroom and outside assignments. And turn those in. So how do we get from those cylinders to where the gas needs to be in the hospital? In this case, what you're looking for are their long-term care facility. In this case, we're looking at our piping system. And again, the National Fire Protection Agency governs the construction, installation, and testing of these systems. Your pipes are seamless K or L copper tubing or standard weight brass. They have to conform to good manufacturing practices, okay? They also have to be clean and sealed prior to delivery. And they're going to be checked once they arrive where they are to be put in so that you can make sure that everything is where it's supposed to be and how it's supposed to be. So after installation, the system has to be pressurized to 75 psi for 24 hours. What we're trying to find out with this is, do you have any leaks in the system? Is everything the way it's supposed to be? Are all the joints sealed like they're supposed to be? Is the copper the right standard weight copper? Was there an accident on the way to the facility and that the material got bent or something? And so we need to make sure that everything is going to work like it's supposed to. What we pressurize it with is nitrogen. And there it is. We're looking for leaks. And then you label every 20 feet with a type of gas and at least one in each room. And then if you're going up above, it has to also be labeled as it goes up above the different stories. And there it is, the pressure regulating device between the bulk system and the main. The supply is a minimum of 50 psi to all station outlets. So remember, our working pressure of our gas, 50 psi, okay? What's interesting is we actually had a student one time who was telling us that he was working in a new hospital. They had installed the O2 piping system. They supposedly had gone through all of this at this point. Supposedly it had also been analyzed. They were having a surgery at that particular point in time, and the patient was a 3-year-old child. Unfortunately, what was coming out of the oxygen piping system was nitrous, and unfortunately the child died as a result of it. How it got around, it's hard to say because they're all supposed to be analyzed. So whoever makes sure that that stuff is done needs to make sure that they take it very seriously. Okay. And then there is a visual inspection. Again, make sure everything is where it's supposed to be, that it's all set up like it's supposed to. If you are the director of a department and there's a new part going into the building, or you're getting a brand new building, this is going to be part of your responsibility to make sure that you understand how these piping systems work and what your responsibility is to make sure your patients are safe. So there's 4 main pressure alarms, or 4 main alarms, let's put it that way. One is the main pressure alarm. It tells you there's a pressure drop or interrupted flow at that point. In the larger hospitals, it's normally at the switchboard because you have an operator on duty for 24 hours a day. They're told how to do this. They're told who to call and not to shut it off because it's annoying. In some of the smaller facilities, it's at the nurses' station. Hopefully, you guys have briefed the nurses that they have to make sure that they know what's going on at that point, or even the patient care techs that are there at that point to make sure they understand not to turn that off, but to come and get you. There's a main shutoff located outside of the building, and so you need to make sure that you know where that is so that you can shut the system down if you need to. Zone valves will shut off different areas of the hospital. I'm going to show you one that's a little bit old. If you visited somebody in the hospital, you would have noticed on the wall that there's this little, be like a little box or something, and you'll see 3 little, now we know what they are, dis outlets in it, labeled for oxygen, medical air, and vacuum. Oxygen is green, medical air is yellow, vacuum is white, and that's your vacuum system. That is your zone valve, okay? And then the riser valve shuts off the floors above the main floor. Always kind of interesting, if you go to Chick-fil-A and you're going through the drive-in, if you look over on part of the building, you'll see a riser room. If you go to Starbucks, we're next to the Hooters on Broadway. If you look, you'll see that one of theirs is also located and says riser room. And that would be for anything that's above the main floor at that particular point. The station outlet is a station outlet. It's not part of the safety system. The station outlet is where this gas is coming out of it, okay? And this is where we're going to find our disconnectors so that we can hook up our equipment. So basically, there you have it, the main pressure alarm, the main shutoff, the zone valves, the riser valves, and the station outlet is not part of this system. This is an older zone valve, but you can see it's the same type of design. There's your oxygen, there's your medical air, and there's your vacuum. And the vacuum is just pure white, as you can see. And at this point, you can see the zone valves. They would be cutting off the various portions going to the different hospital areas. There's the riser. It's cutting off anything above that first floor. And there's your zone valves, again, just to show you that at that particular point. And just to sum up all the formulas for you, here's something you want to think about until you're comfortable with these. And then even if you're comfortable, do it. Always write your formula at the top of the page, okay? And then you have something to look back. Now, what happens on occasions is when I give folks problems to solve, I get the gas cylinder using for the liquid system, or I get the liquid system trying to find for a gas cylinder. One of the things you need to think about is this: the gas cylinders are A, B, C, D, E, F, G. Liquid systems are liquid systems. So when you're reading a problem and it says you have an E cylinder, that should trigger your mind to tell you, oh, I have a gas. If it says, here's the weight of this system, that should trigger in your mind, this is a liquid system, okay? But once you get to this portion of it, these beyond are all due, okay? So you see, if you take and go to the attendance assignment under course content, you'll see which of these that you have to do, okay?